Today, I'm glad to introduce our recent research on cherries. In this research, we aim to assemble a high-quality chromosome-scale genome of Prunus tomentosa, a cold-resistant cherry species, and to investigate its genetic diversity, structural variation, phylogenetic relationships, and the regulation mechanisms underlying its cold stress adaptation. Prunus tomentosa has been a component of the Chinese diet for over 2,000 years. It's known for its rich vitamin and antioxidant content. It has long been classified within the subgenus Coreus, yet its genetic background remains largely unexplored due to a lack of high-quality chromosome-scale genome studies. Other than the classification, the species is highly cold resistant, surviving extreme temperatures as low as -40 Celsius, making it widely distributed in northern China and other frigid regions. However, the mechanism behind its cold tolerance remain unclear. To bridge these gaps, we successfully assembled a high-quality genome of 211 MBs with a scaffold N50 of 225 MB and a contact N50 of 3.4 MB. This research lays the foundation for deeper genetic and evolutionary studies on Prunus tomentosa. Our phylogenetic analysis revealed that Prunus tomentosa is more closely related to the subgenus Prophora rather than its previously classified subgenus Corosis. This challenges traditional morphology-based classifications and aligns with recent genetic studies. We also identified structural variations across multiple Prunus species, including synaptic regions, duplications, translocations, and inversions. Notably, Prunus tomentosa exhibited 140 MBs of synaptic blocks with sweet cherries. We also confirmed that Prunus tomentosa underwent a whole genome triplication event, known as the Garvar event, which is common among core eudicotes. This WGT event is evident from the case distributions, where we identify the peak K value at 1.22, aligning with the major evolutionary event shared across Prunus species. The centenary analysis reveals a highly conserved genome structure among multiple Prunus species, with clear one-to-one homogeneous relationships. Structural variations such as translocation and duplications highlight key divergence points. The overall gene retention rate for the Prunus species are relatively high and range from 28 to 36%, likely associated with the whole genome triplication event, indicating high genome stability. Multi-omics integration revealed iMP3 and PtMIOX1L as key factors in the cold tolerance of the Prunus tomentosa. The high expression abundance of iMP3 and low expression abundance of PtMIOX1L resulted in high endogenous inositol levels in Prunus tomentosa, potentially conferring superior cold tolerance. The subcellular localization shows that MP3 and MOXL were expressed mainly in the cytoplasm. Then we treated cherry rootstock with exogenous myo-inositol. We find that it can enhance cold resistance in cherry. The results suggest that myo-inositol acts like a protective solute, mitigating RS damage and stabilizing cellular water balance under cold stress. In summary, we assembled a high-quality chromosome-level genome of Prunus tomentosa and clarified its genetic diversity, structural variation, phylogenetic relationships with other Prunus species, and we isolated iMP3 and MOXL1L as key factors in cold tolerance. They maintain higher inositol contents in cherries, potentially confer superior cold tolerance.